Welcome to Calculus. Today we will investigate using Rolle's theorem to guarantee critical points. We'll take a look at two examples where we try to use Rolle's theorems to guarantee critical points, and one example where we try to say, why does the example not apply to Rolle's theorem? Our first example is this cubic function, f of x equals x cubed minus 3x squared minus x minus 1. And we're interested in the interval from -1 to +3. And our task is to find the values of c that satisfy Rolle's theorem. So what we should do first is just lay out for ourselves what Rolle's theorem states. So here's a statement of Rolle's theorem. And essentially there's three conditions to the hypothesis. So if f of x is first of all continuous from A to B, and we'll include those endpoints in that continuity statement, comma, differentiable on the open interval from A to B, and the two endpoints f at A and f at B are equal. So I've got to fulfill those three criteria. The function has to be continuous on the interval, differentiable on the open interval, and the endpoint should have the same function values. The y values of the endpoint should be identical. Then, so here's our conclusion, there exists a number c such that, let's back up for a second, c between A and B, such that the derivative evaluated at c equals 0. Well, let's investigate this particular function, our cubic function, and see if it applies to Rolle's theorem. And then if it does, let's find those that one or more than one c values where the derivative at c equals 0. So let's graph this function just to begin, just to see if we got the continuity, differentiability, and the identical endpoint y values. So I'm going to graph this function by creating a table of values. So x, f of x. And we're interested in the interval from -1 to 3. So -1, 0, 1, 2, and 3. And let's calculate these y values. So I'm going to plug in the x values into the function. So -1 cubed minus 3 times -1 squared minus -1 minus 1. So if I evaluate that all out, -1 cubed is -1, minus 3, that's -4, plus 1 minus 1, this has the value of -4. All right, we'll keep going. So at 0, it's 0 cubed minus 3 times 0 squared minus 0. So those first three terms will zero out. Overall value is going to be -1. At 1, 1 cubed minus 3 times 1 squared minus 1 minus 1. So that's going to be 1 minus 3, so that's -2, minus 1, that's also -4. All right, at 2, 2 cubed minus 3 times 2 squared minus 2 minus 1. So that's going to be 8 minus 3 times 4 is 8 minus 12 is -4, minus 2 is -6, minus 1 is -7. And then lastly here at 3, so 3 cubed, that's 27, minus 3 times 3 squared, that's also 27. So those are going to zero out those first two terms, -3 minus 1, and that's -4. So let's graph this and see if we can apply Rolle's theorem here. So -1, -4, 0, -1, 1, -4, 2, -7, and 3, -4. So if I were to sketch this function with a all real numbers domain, it would have this appearance. that typical cubic function kind of double wave in the middle. But again, we're interested in just the interval from -1 to +3. So I'm just going to restrict the domain here. And let's just check to see if this function satisfies the 3 criteria in the hypothesis of Rolle's theorem. So first of all, we do see it's continuous from -1 to 3. There's no discontinuity. It's also differentiable from -1 to 3. I don't see any corners. I don't see any cusps. So we're good on differentiability. And the two endpoints, if I were to highlight them, show the same y value. They both have the y value of -4. So Rolle's theorem does apply here. So what we can be sure of is that there exists a c, some x value, within this interval so that the derivative of the function equals 0. And remember, what we're saying there is, where does the tangent line to the graph have a slope of 0? So I see definitely here at the maximum at x equals 0, that tangent line has a slope of 0. Also, at this minimum value at 2, the derivative has a value of 0. The tangent line to the original graph at 2 has a slope of 0. So those are my hypothesis. I think that those are the two critical points. Let's prove it by taking the derivative of the function. So you can kind of roughly say, I think that I've found the critical points, but you do want to follow up with the algebraic work. So you take the derivative of the function. That's going to be 6x squared minus, I did that incorrectly. Not 6x squared, 3x squared minus 6x minus 1. So I do want to set that equal to 0 and solve, but what I'm seeing here is that's not a factorable quadratic. So I'm going to use the quadratic formula to solve here. So x equals negative b, so -6 plus or minus the square root of b squared, so -6 squared, minus 4 times a is 3 times c is -1, all over 2 times a, which is 3. So let's reduce that down, see if we can identify these points. So that's going to be 6 plus or minus, if I evaluate that discriminant, -6 squared is 36, -4 times 3 times -1 is positive 12, so that's 48 under the radical over 6, and then 48 16 times 3, so this would be 6 plus or minus square root of 16 is 4 square root of 3 over 6. And then I see I've got a 2 I could divide out of those 3, 6, 6, and 4. So our two critical numbers here aren't where we thought they are. They're at 3 plus or minus 2 square root of 3 over 3. And if I were to calculate those out, those would be values close to what we hypothesized at 0 and at 2. It's just they're not rational. My graph gets points that are close to the max and the min, but just offset slightly. So for my critical points, I just need to adjust here. It's not at 0. So let's modify these two values, and it's not at 2. Let's see where they are. So my first value would be the positive, or it's the 0 one. So this is close to 0, but not 0. It's the minus 3 minus 2 times the square root of 3 over 3. So what we're going to see is that this is actually slightly negative. And then down here below, I've got x equals the positive or the plus version, 3 plus 2 times the square root of 3 over 3. So although we were able to estimate where those values were just from our graph, we do need the algebra to find the exact value of the critical numbers. So let's finalize our answer here, critical numbers. And those are going to be, we could list them in a set as 3 minus 2 square root of 3 over 3 and 3 plus 2 square root of 3 over 3. So that first example was an instance where we were able to apply Rolle's theorem to a cubic, a polynomial function. Our second example is a trigonometric function. So here our original is f of x equals cosine of 2x, and we're interested in the interval from negative pi to pi. So just like we did with our first example, let's begin by graphing the function just to see if it satisfies Rolle's theorem at the outset. Remember, there's 3 criteria. The function must be continuous over the interval, the closed interval. It must be differentiable over the open interval, and the endpoints have to have the same y value. So f at a must equal f at b. So our interval here is from negative pi to pi. So I'm going to put negative pi, place 0 in the center and pi at the far right extreme. And then let's fit in some other values. So I could put negative pi over 2. That's not negative 90 degrees. Positive pi over 2. And then because I've got this doubled x value, my angle is going to double every time I plug in an x value. I should include these intervening ones. So negative 3 pi over 4, negative pi over 4, and positive 3 pi over 4. So there's our x values, our domain values. And let's evaluate and graph this function. So I'm going to start here at 0, just since it's convenient. So I'm calculating cosine of 2 times 0, which is just cosine at 0, which is going to have the value of 1. So as we do with trig functions, I just want to catch the pattern, and then I can use the pattern to extend my y values. So let's calculate cosine at pi over 4. So it's cosine of actually 2 times pi over 4. So that's going to be pi over 2 if we reduce that angle. And the value of cosine at 90 pi over 2 is 0. So I think the next one's going to be negative 1. If we can see that, then we can apply a pattern and just quickly fill in our table. So 2 times pi over 2 is just pi. Cosine at pi is negative 1. So now I can say, here's a pattern, 0, 1, and then if I back up 0, negative 1, 0, 1. Let's plot that function. So at negative pi, we've got a value of 1. At negative 3 pi over 4, it's at 0. Negative pi over 2 is negative 1. Negative pi over 4 is 0. 0 is 1. Pi over 4 is 0. Pi over 2, negative 1. 3 pi over 4, 0 pi, 1. And we can plot our function. So again, we're not going to plot the whole function, just across the domain of negative pi to positive pi. And we get what looks to be a curved W shape. So let's check to see if this function from negative pi to pi satisfies the 3 criteria for Rolle's theorem. First of all, is it continuous? Yes. Is it differentiable across that domain, negative pi to pi? Yes. Thirdly, do the endpoints have the same y values? And definitely, we see that they do. They each have the y value of 1. At negative pi, it's 1. At pi, it's 1. So Rolle's theorem is applicable here, which guarantees that there is a c value between negative pi and pi for which the value of the derivative of the function equals 0. And I see I actually have more than one. If I place some tangent lines, it looks like I've in fact got 3 points. And those, not surprisingly, are the minimum, in fact, minima values, and the one maximum value there in the center of the graph. So my feeling is that we've got critical points at x equals negative pi over 2 and positive pi over 2. Those are the minima. And then my maxima here is x equals 0. Again, that's a hypothesis that I come up with based on the graph and the fact that it satisfies the 3 criteria of Roll's theorem. What I need to do is follow up with the algebra. So remember, Roll's theorem says that if I satisfy the criteria, then the value of the derivative should have at least one critical point there. So f at prime of x is going to be negative sine of 2x, and then I need to use chain rule, take the derivative of that 2x, so it's times 2. So that derivative is going to have value of negative 2 sine of 2x. So I'm going to set that equal to 0, and I want to solve for x. So I can divide over the negative 2 just to dispense with it. That doesn't change a whole lot, just reduces the equation down to sine of 2x equals 0. So we're interested in here really at what angle value will sine have the value of 0. So just thinking unit circle, this angle could be equal to 0, could be equal to pi. And these are values where sine has a value of 0. And since we're including negative values, also could include negative pi. So what we need to do is just solve for those 3. So what I'm going to do is I'm going to take, since this angle is given as 2x, and just creating some related but smaller equations, I want to set 2x equal to these 3 values. So 2x equals negative pi. So I'll just solve there. That gives me this x equals negative pi over 2. And that checks out. I see it on my graph. Let's also set 2x equal to 0. If I divide by 2 there, I get x equals 0. And that corresponds with the critical point where I'm seeing a maximum. And then lastly, 2x divided by, we'll wait on the division. Let me set it equal to positive pi, then divide by 2. And that gives us our third critical point at x equals pi over 2. And for this example, really what we saw in our graph is exactly corroborated by our derivative work here algebraically. So sometimes you win them, sometimes you lose them. Although in calculus, you always win. That's just how calculus works. Okay, so 2 examples we've looked at. One was a polynomial. This one's a trig function. In these, they actually applied Roll's theorem. They satisfied the 3 criteria. Let's take a look at one that, from the outset, we have our doubts. Instructions here state why Roll's theorem cannot be applied to the function f on the given interval. So here we've got a function f of x equals x to the power of 1/3 minus x on the interval -1 to +1. And what I'd like to do is I just want to graph this function. So if I were to create, I could create a table and a graph, but let's just plug this one into our graphing calculator. Since it'll give us a convenient view. So it's the function f of x equals x to the power of 1/3 minus x. And we're going to restrict our domain from -1 to 1. So we'll head over to our graphing calculator to Desmos. Let's just put in that function. So f of x equals x to the power of 1/3 minus x. So we get this function that looks like linear almost, but it's got a double wave in the middle. And let's restrict our domain. So we're going to restrict it again from -1 to +1. And then we got our graph that's been restricted there. I'm just going to zoom in so we can see clearly whether or not this function satisfies the 3 criteria of Roll's theorem. So first of all, is it continuous on its domain? And yes, there's no discontinuity here. Everything is defined. Secondly, we're interested in whether or not this function is differentiable across the domain. And this is where we are seeing kind of a shortcoming. If I investigate this center of this graph, where the graph passes through the origin, the derivative for the function right here is going to be a perfectly vertical line. And so what we would say is that the slope of the tangent line at 0 for this function is infinite. Let's go ahead and just place it. It is the line x equals 0. And because the tangent line is vertical here, the function is not differentiable at the x value of 0. And so although this function satisfies the first criteria, it fails the second criteria, the differentiable criteria in Roll's theorem. We can check the third criteria. Do the endpoints have the same y values? That actually also satisfies the theorem. The value of the function at -1 is 0. The value of the function at 1 is 0. So again, although it satisfies the first and the third criteria, it fails the second criteria. Let's go back to our notes just to finalize that answer. So we can make a quick sketch. -1, 1, and here's our function again. Decreases, goes steeply through, and then decrease. So again, let's write in words why this does not allow Roll's theorem to be applied. So the function is not differentiable at x equals 0 because the value of the derivative at 0 is infinite. Although the function is continuous on -1 to 1 and f at -1 equals f at 1, which is 0, Roll's theorem cannot be applied. And just again to end with a generalization, because the differentiable criteria is not met. And that concludes this investigation of stating whether or not we can apply Roll's theorem to given functions on a certain domain interval. Thank you for joining for this investigation of Roll's theorem. See you soon.